Hey guys, we're going to pick up where we left off at the end of the last video. We were working this last practice problem where we're still working with this equation of nitrogen plus oxygen reacting to form two nitrogen monoxides. And we filled out our ice box and figured out, oops, I forgot an X here, the equilibrium concentrations, or the concentrations of each at equilibrium. First, we had to determine which way the reaction was going. We had to calculate what the K would be, or sort of what the ratio of products to reactants is at this point. We call that the Q because it's not at equilibrium. And this ratio is too high, it's 0.36. And so that means that we need to go in the reverse reaction. That's the direction this reaction is going in. So we use that to set up the icebox, and then we use those equilibrium concentrations and the given K value to set up our equation here. And what we didn't get to finish doing was solving for X. So that's what I'm going to do now. Okay, so the first thing that we need to do is to take the square root of both sides of the equation. The square root of 0.08 is 0.08 is 0.283. And then this side is 0.45 minus 2x over 0.75 plus x. First thing I'm going to do is multiply both sides of the equation by 0.75 plus x. That would cancel it out on this side of the equation. Now I need to distribute, so I get 0.212 plus 0.283x equals 0.45 minus 2x. I'm going to add 2x to both sides of the equation. Cancel it out over here. And I'm going to subtract 0.212 from both sides of the equation. And that'll cancel this variable out over here. So I get 2.283x equals 0.238. Last step is to divide both sides by 2.283. That'll cancel that out, and I get x equals 0.104. All right, remember, when you solve for x, you haven't finished the problem yet. So we have to plug it back in to these equations here in order to solve for the actual equilibrium concentration of each component. So for N2, that was our first reactant, at equilibrium the concentration is 0.75 plus x, and x is 0.104, so that is a concentration of 0.85 molar. And for O2, it's the same story, so it's also 0.85 molar. And for NO, the concentration at equilibrium is going to be, according to the table, the icebox, the E row, it's 0.45 minus 2x, and we plug in 0.104 for our x, and we get a value of 0.24 molar. And that is the final answer, those concentrations at equilibrium for each of those components. Okay, now let's see if I can find page 11 of the notes. It's the next page we're going to. Oh, there it was. Okay, oops. So picking up here in the notes. This is a shortcut method that we're about to talk about called simplifying approximations. And this math, as you've seen, can take up half a page to, solve the icebox, plug in, solve for x, and it can be a little bit time consuming. Well, there's a shortcut that we can use under certain situations, and those circumstances are if the equilibrium constant is relatively small. All right, so for example, if K equals 0.0001, all right, very, very small, and the concentration of the reactants is relatively large. All right. Under those circumstances, we can assume that X is going to be negligible relative to the reactant. In other words, if that X is going to be so small that when we subtract it, like 1 molar minus X, that X is going to be so small that your answer is still going to be 1 molar. All right. So in order for X to be considered negligible, it must be less than 5% of the initial concentration of the reactant. All right, so that might be confusing as an explanation. Let's go through an example problem. In this problem, we have A reacting to form 2B. All right, if we initially start with, we're given a equilibrium constant, K equals 3.3 times 10 to the negative fifth, which is a small number, 0.000033. And we initially start with 1 molar of A. So we'll write out the equation and turn it into an icebox. ICE. All right. So the initial concentration that we're given is 1 molar in A, nothing in B, so 0. All right. So since we're given only reactant and no product, it's fair to assume, the only way the reaction can go is in the forward direction. So if it's going in the forward direction, A is going to be decreasing and B is going to be increasing twice as fast as A because of that coefficient of 2. So at equilibrium, we'll have a concentration of 1 minus X for A and 2X for B. So let's set up our K equilibrium constant. So K for this equation would be B, the concentration of B at equilibrium squared over the concentration of A. And we know for this equation, it gives us that the equilibrium constant is 3.3 times 10 to the negative fifth. And if we plug in B, 2x squared over 1 minus x. All right, since this number here is so small that when we solve for x, x is probably going to be pretty small too. And 1 minus some really small number is still going to be 1. All right, so what we're going to do is we're going to assume here, because this meets the conditions of x being, of k being a very, very small number relative to the initial concentration of A, we're going to assume that X is negligible. All right, and when we do that, what we mean is we just assume, if we assume X is negligible, then we just kind of like cross this part out. Okay, 1 minus X is still going to be equal to 1, is essentially what we're saying. So instead we have 3.3 times 10 to the negative fifth equals 2x squared over 1. Now this is a lot easier to solve. All right, so now when we solve it, it's just 3.3 times 10 to the negative fifth equals 2x squared, which is, I guess, is 4x squared, because it's 2 squared and x squared. So now we just divide both sides by 4. And I'm moving this to the next page. Let me actually just move this whole thing. I'm going to rewrite that out. So we had 3.3 times 10 to the negative fifth equals 4x squared. 2x in parentheses squared is going to be 4x squared. Divide both sides by 4, and we get 8.25 times 10 to the negative sixth equals x squared. And then take the square root of both sides, and you get x equals 0.00287. So that's our value of x. All right. We do need to check. The third thing we need to do is, or not the third thing, we need to check though, if this is valid. Check if X approximation is valid. Remember we said that you can only use this shortcut if X is less than 5% of the concentration of the initial concentration, in this case the concentration of A. Okay, so let's double check and make sure that's true. X is 0.0287. Our initial concentration was 1 molar times 100% gives us 0.29%. All right, so that is well under 5%. So using this X approximation, in this case, X really is so small that we can consider it negligible and use this shortcut. So we can use this value of X, and we can say that our concentration of A at equilibrium was going to be 1 minus X, and that X was so negligible, it's still 1 molar. And the concentration of B at equilibrium was 2X, which is 2 times 0.00287, which is equal to 0.0057 molar. All right, I carried my X out 3 significant figures because my ultimate answer should be rounded to 2 significant figures. So it's always nice to, don't round to 2 significant figures till you get to sort of the end of your problem. Okay, so this one is for you to try. Feel free to pause the video and try it on your own, but I will work it for you now. So now we have a new reaction that we're working with. 2H2S reacts to form 2H2 and S2. All of these are gases. This is a homogeneous equilibrium. We're given an equilibrium constant of 1.67 times 10 to the negative 7th, which I'm noting in my head right away is a very small number. So I think I can probably use the X approximation shortcut. I have a 0.5 liter vessel. It initially contains 0.0125 moles of H2S. Find the equilibrium concentrations. Alrighty, so I'm going to go ahead and write out the equation. 2H2 plus S2. I'm going to make my ice box. I like doing it in blue because water is blue and ice is frozen water. That's my rationale. Okay, it doesn't give me an initial concentration, but it does give me moles per liter, so I can easily calculate the concentration. 0.0125 moles per 0.500 liters equals a concentration of 0.025 molar. And I should carry that out one more significant figure. 0.0250 molar, technically. All right, it doesn't mention anything about any products being present. So we only have reactants, no products. If we only have reactants, then the reaction has to be going in the forward direction, which means we will be losing reactant. The amount of reactant will go down, in this case by 2x because of that 2 coefficient. The amount of this product will be going up by 2x, and this one will be going, this will be going, up by 2x, and this one will be going up by 1x. Okay, so at equilibrium, we've got 0.025 minus 2x, and this one will be 0 plus 2x, which is 2x, and this one will just be x. So our equation, our equilibrium constant expression here is going to be H2 squared times S2, the concentration of the products, over the concentration of the reactants. This will be squared as well. We're given a K value of 1.67 times 10 to the negative 7th. and we can plug in those equilibrium concentrations we just figured out. So this will be 2x squared times x. These are just coming from there. And the reactant concentration at equilibrium is 0.025 minus 2x squared. All right, so in this case, again, our equilibrium constant is so very small, we can assume that x is negligible. Oops, I'm trying to scroll. All right, so let's assume x is negligible. All right, so if we do that, anytime we're subtracting x from another number, we don't count it. So in other words, we're just going to say this minus 2x is not going to make a difference in this number here. All right, so if we assume x is negligible, now let's solve the problem. So we've got square root of both sides. Oh wait, no, I don't want to do that yet. Okay, so next I'm just going to simplify this. So I've got 1.67 times 10 to the negative 7th equals 4x cubed, because I've got x squared times x, so I've got x cubed, and 2 squared is 2, so I've got 4x to the third over 0.025 squared, whatever, I'll just write that out, 0.025 squared. All right, now I'm going to multiply both sides by 0.025 squared. Cancel out over here. 0.025 squared times 1.67 times 10 to the negative 7th is 1.04 times 10 to the negative 9th equals 4x cubed. Divide both sides by 4. That cancels out. And we get 2.6 times 10 to the negative 10 equals x cubed. So now we take the cube root of each side, and we get x equals 6.38 times 10 to the negative 4. All right, we must check the validity. In other words, make sure that this is less than 5% of our initial concentration. So 6.38 times 10 to the negative 4 divided by the initial concentration, which was 0.025 molar, times 100%, and that equals 2.6%, which is less than 5%. It's less than 5%, so it's kosher. Using this x shortcut, x is negligible shortcut, was kosher in this case. So lastly, we need to write all of those final concentrations, or sorry, equilibrium concentrations. So I need to remember up here my equation. So our reactant H2S, all right, was equal to 0.025 minus 2x. All right, 2 times that x is still going to be negligible, so it's still going to have a concentration of 0.025, or I suppose it should be 0.0250 for proper sig figs. And then our products, which are H2 and S2, at equilibrium, H2's concentration is 2x, which is 2 times 6.38, excuse me, times 10 to the negative 4th, which is going to be 1.28 times 10 to the negative 3rd molar. And the concentration of S at equilibrium is just X. So just 6.38 times 10 to the negative 4th molar. All right, so believe it or not, there are cases in math where these problems are even more complicated, where you end up with, when you're solving for x, you have an equation where you need to use the quadratic formula. For simplification, I have problem set. I don't have them in the lecture. We're not going to do problems that require the quadratic formula. And I just want you to know that it's out there, it exists, it's sort of the next level of the problem. But for keeping it simple, making sure you understand how to do this process, I didn't want to add that extra level of complexity of math. So just know if you come across that in the reading about quadratic formula or in some of the videos that I played for you, you are not going to be responsible for any of those in the homework. But if you are comfortable with quadratic formula and good at algebra, I encourage you to try some of those problems, especially if you're going to be going on to take more chemistry. It's not a bad thing to know, but just know on the test and on the homework, I'm not going to be asking you to use the quadratic formula. I will be asking you to solve for x, either longhand or using this x is negligible shortcut. Okay, page 13. This is a quick concept check question. All right, so for a generic reaction, A reacts to form B. Consider the following K and concentration of A values, and then select which one. X's small approximation would be appropriate. Okay, so remember, we can use the X's small approximation when K is very small and A is relatively large. Generally, a difference of 1,000. So A needs to be 1,000-fold greater than K. All right, so A here, 1 times 10 to the negative 5th is very, very small, 0.00001, okay, versus an initial concentration of 0.25 molar, okay? This is more than 1,000 times greater, so this is one where it would be kosher to use. In B, I think this is supposed to be a positive 5, 1 times 10 to the 5th, not negative 5th, and an initial concentration of 0.25 molar. So this one would not work because K is very large. All right. In C, we have a small k again, 1 times 10 to the negative 5th, but A is also very small. There's not 1,000-fold difference between these two. There's like 2.5-fold difference, okay? So this situation would not be appropriate to use that X approximation technique. X would not be negligible. And then lastly, K is 1.0 times 10 to the 5th. Right away, I'm just going to say no because that K is pretty large. I can't imagine a concentration being larger, 1,000 times larger than that. So the only time that it's appropriate in these circumstances would be in scenario A. Okay, really last topic here in the chapter is about shifting equilibrium. So you can have a reaction that's at equilibrium, but then you can mess with it. What if you have a reaction at equilibrium and then you decide to add more reactant, or you remove some product, all right? When you mess with a reaction that's at, I sort of think of equilibrium as like, it's doing yoga, like and it's at peace, and then you like go and shove it, and then it's not at peace anymore. So the person who sort of came up with these rules or recognized the way that reactions will shift based on different stresses was named Le Chatelier. All right, so Le Chatelier's principle states that when a chemical equilibrium is disturbed or stressed, the system will shift to restore equilibrium. All right, that chemical reactions are always moving towards equilibrium. They're always trying to get to an equilibrium state. So some of these disturbances can include changing the reactant or product concentration. Again, this is only relevant if they are aqueous or gaseous, because those are the only two states that have concentration. Another way we can disturb them is by changing the reaction volume or pressure, and this is only relevant for gases. So changing the reaction volume does change the pressure. Another way we can change pressure is by adding an inert gas, and I'll go over that. And then we can also change the temperature. Changes in temperature will also affect the shift of the reaction. Depending on whether the reaction is endothermic or exothermic, it will determine which way it shifts. So let's start with changes in concentration. All right. If you increase the concentration of a substance, then you are going to shift away from that side. All right, so I like to say if you add more reactant, you're going to shift the reaction this way. If you add more product, then you'll shift the reaction that way. You're going to shift it away. All right, which makes sense. If you add more reactant, now you have more stuff, you have more reactant to make more products. So you're going to shift it towards products and vice versa. Sorry for the interruption there. Okay, and the other thing is if you decrease the concentration of a substance, then you shift the reaction toward that side. So if we were to remove reactants, we need to replace them and make more of them by shifting the reaction towards the reactants. If we were to remove product, then we need to make more product and shift in the direction toward the product. So these are sort of my mnemonic rules. If you increase, you shift away. If you decrease something, you shift toward. Let's practice this. Oh, oops, nope, I got a couple more things to talk about. All right, changes in volume / pressure. And this is only for gases. Gases only. Okay. If you increase the pressure or decrease the volume, same thing. So in this picture here, if I increase the pressure on this piston, I'm going to decrease the volume. I'm going to push it down. Okay. Then we're going to shift to the side with fewer moles of gas. All right. In this equation, we have 1 mole of gas, 1 mole of gas, 1 mole of gas. So this is 2 moles of gas on this side and 1 mole of gas on this side. These reactants are combining when they form products. So there's fewer moles of product than there were of reactant. All right, so if we increase the pressure here by decreasing the volume, we would shift it towards the product side because that's the side with fewer moles of gas. If we were to decrease the pressure or increase the volume, we would shift it to the side with more moles of gas. We'd shift it in the other direction. All right. And then lastly, changes in temperature can shift the reaction. All right. If we increase the temperature, then it's going to favor an endothermic reaction. And if we decrease the temperature, it will favor exothermic reactions. If we write out, so remember, endothermic reactions have a positive enthalpy. We can think of them as they absorb heat or they need heat. So we can think of heat as a reactant. So we can write heat with the other reactants. All right, for an endothermic reaction. And for an exothermic reaction, it releases heat. So we can think of heat as sort of like a product. And if you think of heat as a reactant or a product, then it works very similar to the change in concentration rules. If you add heat, all right, to an endothermic, if we're talking about endothermic reaction, if you add heat, you're going to shift it to the opposite side because heat is a reactant. And when you add something, you shift it away. All right. If it's an exothermic reaction and you add heat, you're going to shift it toward the reactant side. You're going to shift it away from the heat, which is on the product side. Okay. And for this last problem here, give this a try and I'll write the answers and I'll take a screenshot and send it to you because my video is going to cut off right now.